Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. Now, if you have any questions throughout the session, this is a pre-recorded session this week. So if you do have any questions, if you're joining us on Zoom, just reply to the confirmation email that you got when you signed up for the class, and we can answer those. If you're watching on YouTube, just leave a comment underneath the video. And if you're watching on Facebook as well, leave a comment under the video, and I'll get to those when I can. So my name is Jason Gabrinas. I'm one of Snap-on's national diagnostic technical trainers. Been in the training department the last 11 years or so, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, I was a couple years as a diagnostic sales rep with Snap-on, so I had about 30 different franchisees I worked with, as well as the shops that they service in order to help everyone get the most out of their diagnostic needs. And before that, it was 8 years at Subaru, so worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up with the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bay. And before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is cam and crank correlation. Now, we've talked about cam sensors and crank sensors previously in the past. And really the important thing to test when you're testing the cam and crank sensors is not just whether or not the pattern's working, which is just part of it, but also, is my timing chain stretched? Did my timing belt jump a tooth or what have you? So you can see whether or not they're in time and whether or not the cam shaft is advanced or retarded or what have you. So first off, let's recap what kind of cam and crank sensors we have out there, and there's different ways of testing these depending on what style of sensor it is, of course. So we have a magnetic pulse generator, which is going to be analog, and we have a Hall effect switch, which is going to be more of a digital square wave. And then we also have a magnetoresistive sensor, which is going to work similarly to that Hall effect switch, but a little bit different. So magnetic pulse generator, that's usually going to send out an AC type sine wave type signal. So it's an electromagnet, but it is a passive electromagnet. So it's a magnet with some coil around it. And when the metal of the crankshaft goes by, you can see it's got different teeth on this. And whenever a tooth goes by, it induces a voltage into that, and then it produces a pulse like this. So it's going to look similar to this. And as I said, it's an induced AC voltage output, so it generates its own voltage. The voltage output is relative to the engine RPM, so it is going to increase the faster the engine goes. They will also get closer together, the pattern, as the engine goes faster. The coil winding polarity is designed for that specific application. You can't reverse the leads, so it only plugs in one way. And it is a two-wire sensor. No power, ground, and signal. It's just positive and negative. On a Hall effect switch, it's a little bit different. So it is a toggling DC voltage output. So you're going to see more of a square wave in that case. The signal is not engine RPM sensitive. It's very stable at a very low speed. So you'll have a steady voltage, but the time will get compressed the faster the engine goes. So as the RPMs increase, the frequency will get faster, but the voltage will stay the same. Is most commonly a 3-wire sensor requiring voltage, feed, and ground to operate. And some dual units will have 4 wires and 2 output signals, as we see in this case on this old school distributor here. That actually goes from the pickup coil in that. So speaking of those, had a interesting case a few years ago. I was on a 91 F250 with a 5.8 liter engine. And on those, it has the distributor on the front, and it also has the old school ignition control module, just a little EEC4, EEC5, I guess, on those, and the modules that would always fail when they plug in. But this truck would fail, and it would stall occasionally, and it didn't really matter whether it was hot or cold or the amount of time passing. So they suspected, maybe it is the ignition module, but how do they know? It could be the crank sensor too, or it could be a host of other things on the vehicle. So that we wanted to check. So we decided to use correlation, not necessarily cam and crank, but the crank position sensor is part of that, or there's an output for the crank position sensor on that distributor. Right. So you have the crank position sensor, which would be your pulse out to the computer. Then we have what's called spout on that system, which is the spark out. So that's a signal out of the computer back to the ignition control module to fire the ignition. You see how it kind of uh, correlates there, right? So we got a 0 volts right there, and that's when the well starts, and that's when it fires, right? So we can see the when that coil needs to fire, it's going to send that signal. So what failed? Did anything fail? So we recorded the lab scope pattern until the vehicle shut off, and then we zoomed out on the pattern to see kind of who failed first. And what we were able to find out was, well, this is the crank sensor. Right? It's going to be a square wave. It's a Hall effect. And then that's heading to the computer, right? And then the computer is going to send out this spark out back to the control module. And then the control module has to send this signal out to the coil. And lo and behold, would you look at that? Quite a bit of time also between when that coil output stopped and where the vehicle actually stalled, which is over here. And you can see how it got slower and slower as it stalled. So they're going to get further and further apart, just like you would expect. But in this way, we were able to tell, well, was it the crank sensor? Was it the computer? Or was it the actual ignition module, which it was the module, because the module wasn't spitting anything out. But the computer was getting crank signal and it was sending the signal back. So that means, well, it needed another module. So that's just one way of looking at the interrelationships between cam, crank, and other things on the vehicle. Now, with modern vehicles, newer than a 91, you're going to, of course, see more complex systems, more different types of cam and crank sensors as well, and multiple cam and crank sensors on these vehicles. So here's another example. This is on a Subaru. So this is your Hall effect type sensor as well. So it's going to have a 3-wire connector there, and it goes into the chain cover in the front of the engine. We have a chain cover, and then we have these. So there's your sensor, and then there's a little sensor wheel on top of the camshaft, at the end of the camshaft that it reads. So it's, in this case, it's active. It generates a magnetic field when voltage is applied. And I know it's not exactly what a magnetic field looks like, but it's closest I could do it in PowerPoint, right? So it generates a magnetic field, and then you see as it spins by, it's going to generate a pulse because of how it is changing that magnetic field. Now, that brings us to a different style, which is going to be our magnetoresistive sensor. So typically in this case, it's a 3-wire sensor. It's going to be a digital output like the Hall effect switch. And it's also very sensitive to damage. So trigger wheel imperfections will cause sensor noise. So the trigger wheels themselves on these, it's actually a magnetic encoder ring. If you watch the ABS episode we did a few weeks ago, we talked about magnetoresistive sensor, wheel speed sensors. It's going to work in a very similar way. So in this case, PCM does not supply the 5 volts. A magnetoresistive sensor pulls up 5 volts and then toggles down to ground. And where you're commonly going to see this is on, for example, a very high failure rate on these is the Chrysler, the 3.6 Pentastar engine that they have. So these two things on the end of the camshaft are going to be the encoder wheel. So it's a bunch of north-south magnets that kind of rotate. And then this, the magnetoresistive sensor then picks up that signal and sends it out to the computer. Now, you'll see how they're kind of in here, and that would mean they can be bathed in oil, as it were. But if we have a failure in the system, such as rockers, in this case, you can see the wear down on the rockers, so that is going to give fine metal filings. And what did I say these, well, I can go forward, I guess. What did I say these are? They're magnets, right? North and south poles. So they're going to attract all those metal filings to them, and then they get all gunked up, and then you will have cam sensor codes. And you can replace the cam sensor all you want. It's not going to help until all of that metal is cleaned away. And even still, it might still have some issues on those little encoders. Just be aware if you get one of those with a cam sensor problem, highly likely that it could be an internal failure and you're going to have metal on those encoders, and you would have to make sure everything gets cleaned up sufficiently before it's going to actually work. So I mentioned it a little bit before. Why use multiple channels? So I can compare things on the same time base. And that's one thing that we do with our scope is, everything's on the same time base. So you don't have to worry about, setting that part of it up. And then you can just see and look at the comparison between, say, the cam and the crank in this case. So we can see right here, we got a 2-channel scope. We got the crank sensor is in yellow, and then the cam sensor is in green, and we can see how they line up in these little windows. So cam crank correlation, not every manufacturer, unfortunately, not every manufacturer publishes what a known good pattern is. But in this case, the one we're going to look at today is on a Subaru, and luckily in a bulletin that they have, they actually published a known good cam crank. So in this case, we got the crank sensor on channel 1, right side cam sensor on channel 2, left side cam sensor on channel 3. And you see on the crank sensor, it's got a double gap and a single gap and a double gap and a single gap. So that is one side of the crank sprocket is going to have 2 openings, and then the other side, 180 degrees off of that, will have a single opening, and so on and so forth. And then you'll see there's a gap here, and there's a blip here. And then there's a single gap, blip, gap, double gap, blip, blip, single gap, blip, blip. So between these 3 sensors and the combination of these 4 different patterns, that is how the computer knows when to fire what cylinder. And if we take a look at this, you will see if you drew a straight line through all of those, I think you would agree that they all line up. So this is a good example of a known good cam crank correlation pattern. So if everything kind of falls where it needs to, then I'll know I'm in time. So another detail of this, there is a window that the computer is looking for that pulse to happen and that empty to happen. So as long as it happens within that window that it's looking for, then it'll know it's in time. And it can advance and retard a little bit as in through normal vehicle operation. But if it's too far out, then it's going to misfire and you're going to have timing issues with that. So how would we hook this up? How would we set this up? Because a lot of folks ask when I talk about these things, here's how we're going to set it up on the scope. What I don't really talk about is how do I connect it to the vehicle. So I actually took some pictures this time on this one. And, here's my vehicle. So we have a cam sensor there. We have another cam sensor there. It's kind of hidden behind the oil cap. And then we also have ground, and then the crank sensor. To access the crank sensor, it's actually kind of underneath the intake. It's on the bell housing, so it's kind of hard to get to. So we tell you to hook up over on the engine harness. You can just back probe it there. It's right on top, easy enough to get to. And then, of course, the USB cord would need to go out to the tool. And then down here, I also have a 4th channel that I added for a trigger. And we'll talk about why trigger is important a little bit when we go live on the tool. So a little closer look. That is the crank sensor right there. Like I said, it's right on top, wire number 3, really easy to get to. And then the cam sensor on the passenger side, it's a back probe right there. Driver's side, same thing, back probe there. And then there's my ground on the alternators, as close as I could get because the battery's on the other side of the vehicle. And then, put the scope module in a nice safe place because I'm going to drive this, so I don't want it falling out in the road or getting into the belts or anything. So I just kind of tucked it in between the air filter and the power steering, made it nice and easy. Just it didn't really move. And then, of course, USB cord out through the gasket and then back into the window, and then hooked up to the USB port on the side of the Zeus Plus that I used in this case. So if we were to look at it, we see the crank sensor look kind of like this. Right? So there's that double gap, there's that single gap, and there's that double gap again. So that's one entire revolution in there. And then if we wanted to add additional channels, we can do that as well. So we'll open up the bottom part. So this is a guided component test, by the way. And we'll walk through this, like I said, in a couple minutes. But in guided component tests, some folks think, well, I can't add any additional channels and I can't really do anything with it. It's just one channel, set it, and you're done. And that's not true at all. You can actually add up to 4 channels on our 4-channel tool and change the probes and change the times and change the scales and all of that, just as you would in the scope. It's just preset in this way. So you add a couple more channels. There's one cam sensor and another cam sensor. And then, like I said, you could also do this on a 2-channel tool. You could just do cam and crank, just one cam sensor and the crank sensor at the same time. And then you'd have to switch to the other one. And then, like I said, I also added a 4th channel as a trigger point. So in this case, this is the fuel injector, the number 1 fuel injector, which gives us a reference that only fires once through the firing order. So when that fires, we know that's cylinder 1. And then 3, 4, 2 is the firing order, 1, 3, 4, 2, and then back to 1 over here. Now, this is a little messy. It's kind of hard to see what's going on in there, so we can actually expand that out if we go into our setup view, we can actually separate the 4 channels and make it easier to see. Now, one thing I did want to see with this when I hooked up to the car is, well, I know it's a good running car. I know it's a known good running car, and all of the cam and crank, everything lines up the way it's supposed to. So this is how it would look normally. Now this is just kind of idling, and you see how it's kind of in the middle. This blue channel, so that's the driver's side, sitting kind of in the middle of that window. I marked off the window with the markers there, and then you can see way over here is where the cylinder number 1 fires. So we have this, and then cylinder 1 fires kind of in time with this. Now, as I drove the vehicle, you can see some interesting things happen, because as you're driving, you're going to see the timing is going to advance. So when the timing is advanced, you can see there's my window is much smaller because I've accelerated, right? So my RPMs are faster. The window gets smaller, but where in the window it falls has actually been advanced. So it moved over to the left is going to be advanced. And then you can see how the fuel injector actually advances its firing as well, just to kind of compensate for the increased speed on the engine. Now, if it was retarded, it's not normally, under normal circumstances, it's really not going to retard much, maybe a couple degrees. If I have a problem, then it could be way out, but then it would be over on this side. So I kind of have it centered in the middle under normal operation, idle. And then if you move it to the left, that's advanced. Move it to the right, it's retarded time. So you can kind of see that as you're looking. Now, like I said, not every manufacturer gives you a known good or where it's supposed to be. Other manufacturers, and actually inside the tool on some vehicles, we have that information as well. So let's take a look at that on a Zeus. So in here, first thing I want to talk about is let's walk through those actual steps of setting up multiple channels using guided component tests. You could do it with the scope as well, but I like the guided component test because it gets me a lot closer to where I need to be to start, and then I can just kind of modify from there. So I have my 2012 BMW here, which is our sensor simulator, waveform generator. So if I go into guided component test, of course, it's going to be under engine. I can do the crank sensor. I could do the cam sensor. I'm going to do the crank sensor first. And then you see we have component information. It's going to tell us all about it. It's going to give us our component, our connector views and such. It's a Hall effect type sensor. It says left rear of the engine block below the starter motor. Sounds like it's not that easy to get to either. You have to remove the intake manifold to gain access to the crank sensor. It's very difficult. So it says to actually test it at the computer in this case. And then if we go into the signature test, that'll give us that crank pattern. So I can come in here, and there's what my pattern is supposed to look like. I hit view meter. It's going to open up, and then there's my pattern there. So I'm hooked up to the signal generator. Now, in this case, that pattern is upside down from what this is. And I'm just going to chalk that up to the simulator being flipped, inverted. So that's what we're looking at. But other than the fact that it's flipped upside down, we can actually see that. There's a larger gap, and then there's actually a small gap right before that larger gap, which indicates that's top dead center. Now, if I wanted to add another channel, I'm going to make my meter bigger, make it easier to see. I'm going to come down here, and I'm going to find my additional channels. There's channel 2. And I can see that I got a little bit of a signal down here. Now, why can't I really see that? It's because it automatically sets to 400 volts. So in this case, I can go in there and change it back down to 10 volts because I know it's a 5-volt signal. And we can see the cam sensor and the crank sensor. Now, it is kind of hard to see as they're going by. So another thing we could do to help mitigate that, other than changing the screen view, is we could either add another channel with a trigger. So in this case, I have it hooked up to the fuel injector as well. And now I have a third channel here with the fuel injector. Now you see everybody's kind of moving along at the same time. So if I come over here, you see my trigger is on channel 1. So I can come down here, turn my trigger on to channel 3, and then it's going to lock it in place and locks everything together. So if it's a signal that only happens one time per firing order, like the injector or a coil unplug or something of that nature, you can use that as a trigger and everything will lock in place with each other on the screen, which makes it a lot easier to compare. Now, if I move it over a little bit, we can see there's my gap there, there's my gap there. So that's one complete revolution of the engine. Now, of course, to get through the firing order, we got to go twice. So I could move this out a little bit. I could go to like 50 milliseconds and get a little bit more on the case there. So there's one revolution. There's the second time around there. So that's one actual complete firing order there as it goes around twice. So it's 720 degrees. And then we can see where the cam sensor falls as well. Now, in this case, this is A, they don't publish known good for this, and B, these aren't in time in relation to what you would see on the car, just because of the way the simulator is set up. They're just not set in time. But you wouldn't be able to look at this normally on a vehicle. You'd be able to look at this and see, okay, well, it's like certain number of teeth. Usually, so it's okay. So we want to see a small blip, 6 teeth after the top dead center, or whatever it happens to be. I'm just kind of spouting off at this case, but say you needed to count off 6 teeth and then you see it, but then maybe it's 8 teeth over instead of 6 teeth. So that means the timing would be a little retarded. And in that case, I may have a problem with either the belt jumped or something like that. So you'd be able to see based on whatever the manufacturer's specs are for that particular thing. So that's how I would set it up, and that's how I would look at it. But then if we come back over here, we can go into a couple other vehicles. Not every vehicle has this, but I found 3 really good examples in the tool that have it built into the test. So I can pull this 08 Mercedes SLK 55 AMG, fancy car. Load that up, go into engine, and you'll see there's actually a cam crank relationship test in this vehicle. So if I go into that and I go to a signature test, and I come down here, it's going to give me actually what a known good is. So the center of the third cam sensor pulse before top dead center indicator should line up with the fall of the cam sensor as shown on a good running engine idle. So there's what it would look like there. So the third bump before top dead center indicator should line up with this, right? So that's good. So if it's to the right, my timing is retarded. If it's to the left, then my timing is advanced. So I'd be able to see that. So that's on the Mercedes. Got another one here. It's an Audi A3. And that's going to be very similar. The 2-liter. Cam crank relationship again. And in this case, this one also says waveform should line up inside the upward cam sensor square wave signal on every other crank position sensor top dead center indicator pulse. So like I said, it's got to rotate 720 degrees for it to go one time through the firing order. So that's how it should look on this every other top dead center indicator. And it also gives you, of course, the connector view and all that. And then lastly is going to be our Genesis G80, which will give us that same test under engine. And then we have cam crank relationship once again, signature test. And in this case, it does not have it gives us a known good pattern on the screen, but it doesn't tell us where that should be and where that should fall. So sometimes it does, sometimes it doesn't. It just kind of depends on who authored the test, I guess. But it just says lab scope should be used to observe the relationship between the 2 channels. So you can see the 2 channels right there. That's roughly where it should be on a known good running car. It doesn't really give you how many teeth or what have you like some of the other ones did, but the information's still in there. And then I could go into my test and it's going to set up the 2 channels for me, and I'm going to be able to see that on the screen. So that's they've been adding those over the last couple of years or so. So as moving forward, you'll see those on more and more vehicles. But a good rule of thumb is 50 milliseconds or so. And then all of our sensors are going to be 5 volts usually. Could be a 12 volt on an analog sensor. So then maybe you might want to set it up on a 20 volt scale. But by and large, most modern vehicles, it's going to be 5 volts for everything. So whatever channels you put on, just set it to 10 volts. And that way it won't go off the screen as well. And then you can set it up like that. Or just use the guided component test like I just showed, and we can do it that way as well. So that is cam and crank correlation. Let's talk about what we're going to talk about next week. All right, so next week we are continuing our OEM specific training series. We're replaying our GM episode that we did about 6 weeks ago. So as you may or may not know, as we go along, we do 6 classes new, and then we repeat those 6 classes again, which gives you extra opportunities to watch them live, ask your questions, etc. So we're going to be going through GM, what's unique about them, what's unique about as far as scan tool functions and weird idiosyncrasies of the brand and so on and so forth. So same time as always, same place, 6 and 9 Eastern on Tuesday. Go to snapon.com/OT if you want to register and join on Zoom. Otherwise, the 6 p.m. class goes to YouTube, youtube.com/Snap-on Diagnostics. And then if you want to go to 9 p.m., it goes live to my Facebook page. So it's facebook.com/SnapOnJason, all one word, no dash in the Snap-on. Also, if you want to see any of our previous topics in this series, where this is actually number 88 or 89 right now. We have 89 episodes. Anywhere from ADOS to VAG and beyond and everything in between. So it's all free. It's all about half hour, 40 minutes long. Readily available 24/7 on YouTube. If you scan that QR code, it'll actually bring you to the YouTube page and it will automatically subscribe you. So you head over there and check those out. Also, I want to mention we've been doing this email, for lack of a better term, just email campaigns. So it's training emails, right? So technical focus articles, SureTrack blog, quick tips, new product releases, anything like that. If you want to get those newsletters periodically, it's not like we're going to spam you every day. But if you want to get these newsletters maybe periodically, you can hit that QR code and it'll bring you to a form where you can put your email address in, and then you'll be able to get those, those technical emails sent to your inbox periodically. With that, it's time for questions. And as I said earlier, this is a pre-recorded class. So if you do have a question on Zoom, just make sure that you reply to the confirmation email that you got, and they'll get those questions to me. Otherwise, if you're watching on YouTube, leave a comment, or Facebook, leave a comment, and I'll get to those when I return. Also want to mention my buddy Keith, who also does free diagnostics training every Wednesday and Thursday. So it's at 7:30 Eastern, 6:30 Central, 4:30 Pacific time. And it is meant to have the tool in front of you, kind of do a hands-on, watch what Keith does on the screen while you follow along on your own tool in front of you. Keith's been with us for over 30 years. He's a deep well of Snap-on diagnostics knowledge. So definitely worth your time. It is Zoom only, as I said, too. Just kind of have it in front of you. So it's snapon.com/OT to register for that. On Wednesdays, it is on Zeus and Zeus Plus. And on Thursdays, it is on Apollo and Triton tools. So everything from let's set up your Wi-Fi. Then he walks through Snap-on Cloud and Snap-on Profile, Security Link, and all that. And then he walks through Fast Track Intelligent Diagnostics, Code to Completion. After that, that's about an hour for the first part. And then after that, it takes about a 5-minute break and walks through all the scope and meter functions on the tool as well. So definitely worth your time if you want to learn a little bit more about your tool. And with that, I'd like to thank you very much for taking a little bit of time out of your day, spending a little bit of time with me. Hopefully we've got a few more tips and tricks to help work on those cam and crank sensors and how they correlate together. So with that, enjoy the rest of your week. Enjoy your weekend. Have a good night and take care.